In today's lesson, we'll be looking at atomic physics, that is, the physics of the atom. So atoms are the smallest indivisible units of material that maintain the properties of that material. So if you think of a gold bar, if you cut the gold bar in half, then you'd have two smaller gold bars. If you continue cutting, you'd have smaller and smaller and smaller gold bars until you are left with single atoms of gold. And those are the smallest units that you can have and still have gold. Over the years, there have been various models of atoms, and one of the earliest models was to view atoms as a solid sphere of that material. Then later it became apparent that atoms consisted of some positive and some negative charges that were not all uniformly mixed together. And so there was the idea that maybe atoms are a sphere of positive charge that have negative charges embedded in it, kind of like the chips in a chocolate chip cookie. Rutherford later came up with the idea that there was a small positive nucleus because he chucked at very high speeds charged particles at large nuclei and noted the way that they scattered off those nuclei that seemed to indicate that there was this central region that was small and dense and contained all the positive charge that was in the atom. And so his idea was that you had a small positive nucleus with electrons orbiting like planets. Now, the modern view is not as certain about the positions of the electrons and their motion. So instead, it describes the electrons as existing within clouds of probabilities. So these regions describe the places where the electrons are most likely to be, and these clouds of probabilities have different energy levels. Now, one of the experiments that gives us the biggest hint about what's going on inside of atoms is something called the atomic spectra. So normally if you take white light, such as the light from a light bulb, if you take that white light and pass it through a prism or a diffraction grating, it will spread out and you have all of the colors of the rainbow. If you have a gas, on the other hand, and you excite the gas maybe by shooting electrons through it so that the electrons collide with the gas molecules and excite them, then you will get light only at certain very specific frequencies. So here, for example, is the emission spectrum of hydrogen. So if you excite a hydrogen gas, you will get some red light and some cyan and blue and purple. But just these exact wavelengths, only these colors are present. On the other hand, if you take a cool gas and shine white light through it, then you will get those same exact wavelengths subtracted from the overall rainbow of colors. So you'll have just the red line missing and just the cyan line and the blue and the purple. Those lines will be missing from the white light that was passed through the gas as the atoms were excited by those specific colors. Now with hydrogen, it was known that you have these four lines, these four specific colors in the hydrogen spectrum, and the wavelengths are given here. It was also known that they followed this pattern, this Balmer series pattern. So these specific lines of hydrogen are known as the Balmer series, and they follow this pattern where 1 over the wavelength is equal to a number called the Rydberg constant times 1 over 2 squared minus 1 over n squared. And it wasn't known why they followed this pattern, just that they did. So it looked like you're going from a higher value of n to a lower value, to the value of 2. And those jumps between those values of n and 2 were giving you this Balmer series, but nobody knew why.